Hi, my name is Abby DeFranco, and I'm a 2024 Robotics Institute Summer Scholar. In this video, I'll be presenting the poster for my project called Confidence-Aware Classifier Guidance for Diffusion Policies, advised by Professor Andrea Baichi and Gokul Swamy in the Intent Robotics Lab. To set the scene, imagine you're putting away your dishes with your roommate. You might prefer to place your dishes in a certain position and orientation in your cupboard, while your roommate might prefer a completely different arrangement. We'd like to ask, is it possible for a robot to learn from both of these humans, especially if provided with feedback containing information on each person's preferences? And say, if your sibling moved in, how can the robot align with their new preferences? In this project, we aim to answer these questions, more specifically through a behavior cloning lens. In behavior cloning, you begin with a set of expert demonstrations that show the robot how to complete the task. This dataset can include image and state observations to help provide context about the environment and the robot. The robot then learns a policy pi-hat to predict the next actions given what it sees and where it currently is. It does this by minimizing the distance between its predicted actions and the true actions in the demonstration trajectory. In our work, we begin with a state-of-the-art behavior cloning method called Diffusion Policy, which relies on a diffusion process of iteratively adding noise to action samples and learning to remove it. During the training process, you begin with X0, which is an unnoised action history. Then by iteratively adding Gaussian noise, it turns into a noised sample that becomes increasingly closer to complete Gaussian noise as steps progress. The model learns to predict what noise is added to the sample at the kth iteration by minimizing the mean squared error between the actual added noise and that which the network predicts given what diffusion step you're currently on. So why use a diffusion policy as a base model? Well, diffusion models are a flexible policy class that allow us to do easy composition by modifying the energy function used to generate samples. More specifically, it learns what's called a score function, which is an approximation of the gradient with respect to actions of the log probability density function. This score function can be modified in accordance with learned latent preferences. So this raises the question of how can we steer the base behavior cloning policy using human feedback? We do this through what's called classifier-based guidance. In classifier-based guidance, you train a classifier neural network to predict the probability that a certain action sample belongs to a specific class. We call this network P-phi. Mathematically, we compute the log probability density function of the classifier with respect to the action input, multiply by the respective variance, and weight it according to some weight parameter omega. We then subtract this guidance term from the original score function and produce a new score function that will bias sample generation according to the classifier's predictions. At deployment time, our guided policy lets end users guide the policy based on what feedback was received. The main question we're trying to answer here is not only how to guide the policy using feedback, but how to do so in a reliable fashion. That is, given a new user who doesn't align with any prior users the model learned from, how do we prevent it from classifying incorrectly and providing counterproductive guidance? We propose the following alignment pipeline to leverage diffusion policies, classifier-based guidance, and calibration procedures in order to align with as many users as possible while not producing guidance that improperly steers the policy. The first step of this pipeline is data collection. In this phase, we collect demonstration data in the form of trajectories, which are made up of state, observation, action, and label transitions. We use a MetaQuest controller to teleoperate the robot and use two RGB cameras, one of which is a Z camera, which provides an overhead view of the table, and one that is an Intel RealSense camera mounted to the end effector that provides a wrist view. Additionally, we collect feedback in the form of action trajectory suggestions, which in this case are just chunks of future actions taken by the demonstrator that illustrate how they want to guide the robot. The next step of the pipeline is training a base diffusion policy using the demonstration data. Specifically, we take as input a length 2 image history from both cameras, along with the proprioceptive state of the robot in the form of XYZ positions, R6 rotations, and gripper width, and we teach our policy to predict the next 16 actions. We also train a classifier, P-phi, which is trained separately from the base policy, and this takes in images, proprioceptive state, and human feedback in the form of actions the user likes, and outputs class logits. The next phase is deployment time, in which the base policy and the classifier are combined to produce a guided policy. A new user can then provide feedback displaying their latent preferences, and the policy will try to generate actions in alignment with their wants. At the project's current state, we've implemented the baseline structure of the pipeline from data collection to deployment time. The next phase of the project is highlighted in blue, which includes offline and online calibration methods to prevent the classifier from steering the policy when it is falsely confident. Both methods rely on a temperature parameter that strengthens or weakens guidance. Offline calibration occurs during the training time stages. In this approach, we begin with a held-out calibration dataset that is collected from the user. The dataset is composed of inputs to the classifier and the correct labels. Before deploying the classifier to do guidance, we scale the temperature parameter to minimize cross-entropy loss over this held-out dataset. Online calibration also involves temperature scaling, but during the deployment phase. We infer the temperature parameter of the classifier online whenever new human data is received. This would require designing a Bayesian estimate over the temperature parameter and classes given human feedback. If for all classes the most likely temperature parameter is small, then that indicates none of the classes explain the human feedback very well. In this case, the robot either simply relies on just the base policy or the classifier is adjusted according to data from the new user. Now, before highlighting the main findings of our baseline method, I'd like to briefly describe some details of our implementation. Our base diffusion policy relies on visual encoders, specifically 2 ResNet models, one for each camera that takes as input the image data and outputs an image embedding. After being concatenated with our state information, that then gets fed into an MLP architecture. And the noise network relies on this information-rich observation embedding, along with the current noised actions, and then predicts the added noise. When designing our classifier, we found that reusing the trained observation encoder improved classification accuracy, especially early on in the diffusion process when the actions are closer to complete Gaussian noise. Now onto experiments. We ran our experiments on a simple pick-and-place task where the robot must pick up a small blue cube and place it on the other side of a yellow block serving as an obstacle. Our initial cube position is randomized in the space directly behind the obstacle, and the cube orientation is completely randomized. Our demonstrator data is half trajectories moving leftwards around the cube and half moving rightwards. We designed this task specifically so that there are 2 regions of ambiguity where a point could easily belong to either category. The first is during the phase of the trajectory when the robot moves from the home position to the cube, grasps it, and lifts it off the ground. The second is when the robot is above the goal position, moves down, and places the cube. As shown in the diagram, our classifier predictions reveal that the classifier is least confident around these time steps, which is reflected in the lower saturation of the scatter plot points. We also found that as the denoising process progresses, classifier predictions typically begin at around uniform probabilities, which reflects confusion when inputs are noisier and becomes increasingly confident as the action samples get denoised, which matches our hypotheses. Next, our method succeeds at guiding base policy generations according to input feedback. Specifically, when feedback indicates heading more leftwards is preferred, actions are correctly pushed to the left, and the same for the rightwards case. So when does our current method fail? The answer is when feedback is out of the distribution that the classifier was trained on. To illustrate this, we collected demonstration data that goes over the cube while minimizing any rightwards or leftwards swaying in our trajectories. As we expected, the robot was falsely confident, and at points in the trajectory, it classified the feedback as confidently right and other times as confidently left. Rather than improperly steering our diffusion policy, we want our robot to be able to identify out of distribution data, acknowledge that the end user has unique preferences, and then rely less on the classifier during action generation. To accomplish this, our next steps will be focusing on designing the offline calibration and online monitoring procedures and comparing the effectiveness and the pros and cons of each approach. With that, thank you for listening to my talk. This research was made possible through the National Science Foundation M3X grant. I would like to thank Professor Andrew Baishi and Gokul Swamy for their incredible guidance on this project. And I would also like to thank Rachel Burson, Dr. John Dolan, Morgan Grimm, and all the other amazing people who make RISC possible.